大家好，我是国立清华大学电机系黄眼界。今天我们要介绍第17个单元，这个题目是线性偶极天线。这个天线的长度跟之前比起来比较长，所以我们必须考虑到这个天线上头的电流的分布。So, in the first section, I'm going to introduce you a far field theory for this linear dipole antenna. Then, with the theory, we'll be able to look into the antenna pattern and understand how the antenna will radiate. And then we're going to add a few antennas and make it into an array. Therefore, you can see how those antennas could interfere with each other and generate particular radiation patterns in the far field. Finally, we're going to have the review in the end of this lecture. So the section 17.1 is going to be about the far field theory of a linear dipole antenna. And initially, I want you to look into this police car. And you can see that there are a few antennas equipped on this police car. There are long antennas and short antennas. And in this lecture, we're going to look into long antennas, and the length of it is going to be comparable to the radiation wavelength. And the consequence of a long antenna is that the distribution of the current is going to be a function of position on this antenna, because we're going to establish a standing wave for the current on this antenna. And when this antenna length is comparable to the radiation wavelength, then you're going to see that at different locations, you will have different current distribution. Previously, we modeled the Hertzian dipole antenna, and we assumed this dipole antenna is very, very small, which is very small compared to the wavelength. Therefore, we treated the current as a constant in our calculation. But today, we're going to treat this I, the current, to be a function of the position on this antenna rod. So the first step is to write down a formula to describe the current on this antenna rod. Basically, the current will be oscillating up and down on this antenna along this z direction. So this means that we have to write down a formula that describes a standing wave of the current along z direction. And everybody knows that when you describe a standing wave, you use a sinusoidal function. So in this current formula, we have an amplitude Im, and then we write sine, beta, and h minus z. And for z larger than 0, we have the upper part of the antenna, which has a length of h. And for z less than 0, you have the downward part of the antenna with the length of h as well. And important thing is that you need to set a boundary condition into this formula. The boundary condition is that the current is going to be 0 at the end of the rod, because the electron, the current cannot go through this boundary. So if you set the current to be 0 at the end of the rod, then you end up having this expression. And beta here is the 2 pi over lambda, which is the propagation constant in the transmission line, because you have a current wave propagating on this antenna rod, just like transmission line. But the propagation direction can be upward direction, can be downward direction. So you have a standing wave pattern generated on this antenna. So once we have this current expression, then we start to look into the radiation field far away from this antenna. And for example, if we look at this part of the antenna with this current elements, then the distance between the field point and this current element is denoted by this r prime. But we have to have an origin for the coordinates. We always choose the center of the antenna to be the origin of the coordinates. So we have to derive a formula that describes r prime in terms of r. So if this field point is far away from this antenna, we can have this approximation. R prime is approximately equal to the length of r minus a small section of the length right here, which is z multiplied with the cosine theta. So given these two expressions, we'll be able to start to calculate the far field for this linear antenna. Remember that we have this formula from a dipole, Hertzian dipole antenna, which has a length dl much less than the wavelength. So let's just cut this antenna into a small section and then try to describe the radiation field in the far zone as a radiation from a Hertzian dipole antenna, and then we try to sum over all the small Hertzian dipole antenna to form a linear dipole antenna. So let's copy down this formula derived from the Hertzian dipole antenna, and then replace the dl to be a small section dz here. And then also this r is replaced by r prime. We have a formula on the last page for r prime, so we can just copy the r prime expression into this phase term and also this location. So you translate the solution from a Hertzian dipole to this solution. But this is only true for a differential length on this linear dipole antenna. And we also write down the relationship between the electric field and magnetic field. The proportional factor is the intrinsic impedance, because in the far field, the wave is going to look like a spherical wave or a plane wave if R is really big. So the ratio of the electric field to the magnetic field is going to be the intrinsic wave impedance, just like the ratio for the field for a plane wave. So given this, we'll be able to do an integration through the whole antenna rod by integrating the previous equation from minus h to h. We'll be having this far field electric field for this antenna. So I want to draw your attention on this term. This term is quite important because it's a function of the angle and also the ratio of the antenna rod length to the wavelength. And this is called the antenna pattern, which depends on the ratio of the length of the antenna to the wavelength. And also it tells you the directional property of this antenna. So we're going to focus on this antenna pattern in the next session. 所以呢，在这个第一小节里头，我介绍了这个线形的偶极天线的原场的理论。那基本上一个天线在作用的时候呢，我们会把这个讯号送到很远的地方去，或者接收很远过来的天线。所以呢，我们在乎的只是这个原场的这个理论。那一个线形的偶极天线呢，基本上我们说在这个章节里头，我们定义它的长度呢是跟辐射的波长接近，所以这时候在天线上头电流会是未知的参数，我们必须把这个变数呢放到我们的计算里头来。那这个我们算出了这个原场的理论之后呢，会很注重这个 antenna pattern function。这个 antenna pattern function 呢，我们发现呢，它是跟方向有关之外，同时也跟它天线的长度对于这个辐射波长的比值呢有很大的关系。那在原场呢，这个辐射的波近是一个平面波，所以呢，它的电场对于磁场的比值呢，就是我们所了解的 intrinsic wave impedance。所以这是第一小节里头我要介绍的一些基本观念，谢谢。